Agreed, understood. We have no problem with that. The issue is Dominion has a lead in that area, and of course Dominion will do nothing that puts their facility at risk, nor any of the people in the neighborhood or anybody. And so we depend fully on them to make sure that they are very comfortable with anything that happens.
I think Mark will second what I'm about to say, and as will any of the branch chiefs here. The NRC isn't going to approve anything that we think has any
risk either.
Safety risk.
Sure.
Anything more than what you have by putting any Cask on the
Agreed. Understood. And we don't take that lightly either. I mean, we recognize that. But the thing is, when I phrase that, and I think your point is well taken, I need to reword it a little bit. We're going to spend a whole bunch of money on this Cask project, and we want to maximize the science. We want to maximize the data that we pull out of it. And so we're looking for that fine line, so to speak, so that we do get the data that is meaningful to us and to everybody else who has an interest in it without making problems elsewhere. Because sometimes you see it where you're right, where science takes over and you put other things at risk, and that's not what we're looking at doing. We agree.
Just to clarify, will you prevent ground samples or how late was ground sample okay.
You want to do that today or go? Okay, can we deal with that tomorrow if that's okay?
I appreciate the comments you're making with the balance between the traffic science side and the licensing side as well. In general, the samples, the takeaway samples that they are 1, 3, 10. And so the plan is these takeaway samples, these would be helium samples, right?
Right.
Would be analyzed by this mass measurement or analysis. Is that the plan?
And remember, the samples, the effort and time that we put into grabbing these samples, I mean, they're only going to be like 2 1-liter bottles, so to speak, is what we're kind of thinking right now. Those samples are going to be very precious to us. And the amount of money, I don't even speculate how much that we will be paying for each of those, but it's kind of a sobering thought when I do. But anyway, making sure that we get everything out of those, squeezing every bit of data out of those once we do. That's why as we write our test plan on dealing with those and sampling those and testing them, we will pull a team of our laboratories together to make sure that we understand what we want to do is the first issue. And then when we get that plan set out, we will of course present that to the NRC, see if you have any other additions, and then making sure that we assign it to the lab that can best do it also. And so when we get to that point, we anticipate that the exact testing that we do, the laboratory testing, we anticipate sharing that. So if you have input on that, we do. But we will have a pretty good feel for where we want to go, what we believe, between the EPRI and DOE team.
If everything goes correctly, the only thing that you should be pulling out of there is helium, possibly some moisture, because the only radioactive source that's available outside the rod shouldn't be airborne. And so what's going to be the first indicator is your initial radiation scan of the sample bottles. If they're hot, there's a problem.
There's a problem, yeah.
The temperature and pressure, that is continuous monitoring?
The temperature is
Temperature and pressure? In the cavity?
No decisions been made on the pressure yet, but right now the plan, I'm getting the design stage, but we will have thermocouples internal in the cask in specific spots along the assemblies, and we'll talk about that later. And that will be continuously monitored.
part of the reason for this meeting is we wanted to present some of the ideas. When we come out based on the input and the discussion of this meeting, we will update our test plan and start fleshing it out. The first revision of the test plan that we gave, and we understand perfectly what we did, and that is it discusses mostly the why we were doing certain tests, but we recognize also, and it was intentional, we didn't include a lot of data of the what and the how. And so now we are going to go back into our test plan and start including the what and the hows we're going to do. We've already covered the whys, got a lot of input on that, and it will start maturing as we go, as we start learning more and more and more. And so another revision of the test plan will be occurring here shortly.
Move on to the assembly selection. Any other questions on gas
sampling?
Anybody on the phone on gas sampling? Okay, well, why don't we move on to assembly selection? And this was a very interesting exercise that we went through, and how to get the most high burn-up assemblies in there with the different cladding types and the heat output and one of the criteria that we're using is to drive the internal temperatures up to 400 degrees C, which is the NRC threshold. In the end, we selected in the very center of the cask our candidate assemblies, which is a Z4 low 10, 0 low, and 5. And then starting out in some of the earlier iterations, we had other candidate assemblies around that core center of assemblies. And when we did the thermal analysis, it turned out these high burn-up fuels that the cask internal temperatures were only about barely 300 degrees C. And so we had to take a step back and look at that, and we felt that most of the analysis were done at Pacific Northwest Labs with support from Oak Ridge National Labs, and what I'll say is realistically conservative assumptions that were used on the specific fuel that was going into these casks. And so what we ended up doing is having these 4 candidate assemblies of high burn-up fuel in the center, and then we put a blanket of high burn-up fuel around those assemblies that were shorter cooled fuel. So they actually had a higher thermal output. And at the end of the day, right now it looks like our internal gas temperature is about 303 degrees max. And what's limiting that is actually the neutron absorber on this the cask has got its maximum thermal limit before it starts to degrade. And so that's how we notionally selected the assemblies in terms of the heat output and the heat transfer through different portions of the cask and what limited us. And so there was quite a bit of jockeying about what assembly to put in which basket hole and the burn up kind of cooling and all those sorts of things. And this is we had a very good collaboration, I think, the labs with industry and working through this issue, and I think we got to a very good place in terms of specific assemblies in a specific configuration to drive up to a maximum internal heat without threatening other safety components like the neutron absorbers. John, do you want to add anything to that?
I think that covers it pretty well. Basically, the numbers and trying to make sure that good distribution of heat load in there to understand what was causing it or driving it, the heat. And because it's a very well designed cask, it transports the heat out from the middle pretty well. That's why we start looking at the neutron shield as being one of the limiting factors on it.
We anticipate that there may be some more refining. One of the problems we had is, I'll just say, the laboratories were signing a non-disclosure agreement with the fuel manufacturers to get more data, more exact data on the fuel that was actually there. It took us a little bit longer to get our lawyers together with their lawyers together to come to closure, if you can imagine that. But anyway, it just took longer. It just took longer with the laboratories. We did sign it. They did come to closure, and now we are getting the information from the fuel manufacturers. And so as we get that data, we just signed it about a month or so ago. we will get more data from them. We're doing more modeling on that to hopefully become even more precise in our estimate of the temperatures inside. So we anticipate that those analyses are going on right now, and we hope to share that soon. So it was very encouraging for us, actually.
Just curious, what is the decay heat? Because you mentioned 300 seconds.
We have assemblies up to 1.3 kilowatts. Really pretty hot.
So 24.
Yes, but there's a range. But that blanket in particular, I think every one of them is over a kilowatt. Quite hot. And the four candidate fuels in the center, I think, are around 800 watts.
There were two at 800 watts, one's at 1.3, others at about 1 kilowatt. There's actually some of the smaller ones are at 1.5.
At the 1.5, okay. Yeah. So they're pretty hot.
And PNN are using Cobra?
Yeah.
They actually done with both Cobra, SFS, and the Star CCM.
Certainly, you look at the pancakes outside.
The
Pancakes.
This is from poison. I think this is the poison.
I do from poison.
yeah.
It's on the outside. Well, we're worried about the neutron shield on the outside.
Yeah, no. You were worried about the neutron shield.
Yeah, the resin, the neutron shield on the Cask machine.
Right, but, inside, we're putting the pancakes on.
When he refers to the blanket, he's referring to the hot assemblies that are surrounding central zone.
Right. Then you will have the pancakes on the.
Yeah.
So what you do with the neutron, what
We're talking fast about the, you're describing the blanket, what do you?
I thought you were
Answering
asking
another question, are you, sitting against the neutron explosion, the temperature of the boiling place, or the neutron shield outside of the? Oh, the neutron shield
Shielding.
outside.
Yeah.
That is the temperature that
as opposed to the absorber, which is either a metal or a ceramic.
Right, okay, it is the shielding,
Right.
on shielding, not the neutron absorber.
Actually, my question is
on the outside.
whether it's inside the neutron portion. Outside. We have the pancake. You're going to have the neutron poison in all the basket. Right, yeah. And so you put in the pancake surrounding the fuel assembly. No. The blanket is high, turn up, short, cooled assembly. It's a blanket assembly. Not I thought they were talking about not an insulated absorber. Not an insulated blanket. I thought they were talking about some kind of insulated. No, it's just a hydro fuel assembly.
Yeah.
Okay.
Thermally.
Only 4 hydronic assemblies in the middle, or all of them are hydronic.
Well, I think almost all of them are high burn up. Some are shorter cooled than others.
The highest, burn up higher in the center, or they're not necessarily highest.
The highest one is in the center, it's just
Because you said there are 4 in the center.
Right.
There's 4 different the ceramics. Besides, they're cooled longer.
Their decay heat is not as high as around the.
The burn up is not that much bigger.
Probably not that much.
What is your projected profile with this kind of loading? Does it peak near the outer edges of the cask?
The thermal?
Yes.
I'll defer to Johnson on
the
that.
central zone. Trying to make sure that it was, it'll be in the center area.
Even though all those short-lived ones are on the outer.
That's right there.
What's the maximum sliding temperature?
330. Okay.
Yeah, I think it was 330, but this is based on preliminary information, we don't have design details yet. That they mentioned we'll get the NDAs in place. So we have, we did some approximations, but we know that it's, based on some, judgment calls and assumptions, we're getting on 330.
Wow. So where's the pre-study on the decline temperature then close to the limit on neutron shielding? Okay.
That's what we're trying to watch out for. Remember, we're doing our best estimate now.
It looks like a very
Light
low.
will with the design basis license, that's what they need to meet, the neutron shield.
Oh, yeah, but it seems like a very small casualty. And always cut it degree person.
But we're balancing this with the design basis license and analysis as well.
What is your temperature limit? Is it polyethylene, polypropylene, or the neutron shield?
That's what they have to
Resident.
Yeah.
What's the temperature limit?
300 was it? I think
300.
300. Yeah, thank you. 300. Yeah.
Oh, we're under that.
Yeah.
Okay.
Right.
I guess we're not paying about.
333.
We thought it was.
The internal gas pressure is 230 C. Yeah. But the limit on the thermal neutron shield is 300. Yeah.
These high burn-up assemblies in there, how is the heat load that you're putting in this gas now compared to what the license heat load is when it was originally licensed?
The proposed heat load is going to be around 38. I think the original license was licensed for 32.
In terms of you've done the analysis and the dose back at the task. So you'll
We haven't done a dose and then
the thermal.
Just
So on the imagine with the much higher dose. Yeah, I mean, the next step right now, if that's the cycle response. I know what that is. Because radiation is damage is way to those are the considerations. Something temperature and then for the neutron shield. For your I think that goes back to the stem comment. The balance can find a light conviction.
That's a good comment, though, Raj. I think we need to look at that.
Yeah.
Carefully.
Hope to send you something. P&L is working on this right now. It's still in transition right now. We opted not to bring the current one because we know it's changing very soon. And so as soon as it starts settling down and we'll send it in to you guys to look at, so that you have a chance to look at it also. But the analyses are continuing on this topic.
What is the general mix? You have a number of different claddings in there. What's the, you have 32 assemblies. What's the general mix of claddings?
Raj, John's got the map.
Okay, we got 104 cladding assembly in there. This is the highest one up at the 8. Then we have a lot of 5, a lot of Zerlo. We have one low-speed Dirk, and that's pretty much the distribution. So I send you a breakdown if you want it on how many of each. Here's the proposed
So when are you going to have the final loading there?
This is the final for now unless something comes up.
For now?
Yeah. You're going to get the detailed information that shows something.
Well, the reason I'm asking is we're doing our analysis and it's changing.
Yeah.
So it's like,
Well, this is based on the design basis approach.
no,
No,
it's going to be realistic.
Directional loading.
Actual loading is realistic. That's
Using Cobra as well?
no.
What do you?
As part of our task, we're doing thermal modeling also, and we're going to be using the output from the various thermocouples that you're getting as a baseline to benchmark these codes. We're doing it a little bit differently because we're looking at the low end, but we want to make sure that our codes have a benchmark.
We believe we're very close and have proposed right now that we've identified right now. When we confirm with the data that we have from the manufacturers that what we have is correct, then we can share that. And so, like I say, we hope that's within, say, 4 to 6 weeks is kind of what we're looking at right now. And then that will be pretty much our final loading plan. I mean, it's not going to do, we just can't change a whole lot at this point. Once we get there.
That in some of these assemblies, you're going to be removing sister rods for examination, for recharacterization.
For the baseline,
Yeah. When will that decision be made?
Say that again?
When will that decision be made on which how many rods to take from the
We will probably come up with a plan on the sister rod testing when we, again, back to our test plan, we anticipate updating our test plan again and including more data on the sister rods because we were, other than saying we were going to use sister rods, we didn't say a whole lot in our first test plan. We will start putting together the test plan for our sister rods. We've looked at the equipment that we have available to us across the complex, and there's a lot of stuff that we can do, of course. We probably, probably next summer we would have those nailed down. When we submit the license amendment request, when Dominion submits that, I would hope we would have all our pins located and identified. And
6 months from now.
Yeah. So we can show how we'll establish the baseline with the assemblies that we're going to do. Once we identify the assemblies and lay that out carefully, then we'll start deciding which sister pins we need. Because we need a good baseline on this one. So we'll start picking those, like I say, soon. When we say this is our loading, then we'll start deciding our sister pins to come out. And it shouldn't take us that long. I say 6 months at the max, but it should be a lot before that. I'll ask John. How long what would you estimate?
I think it's done quicker than 6 months. We've been,
Give me a time.
we could do that in 2 months.
Okay. So shortly after the first of the year, then.
The models are already built and everything. So.
Yeah. Understood.
Probably the test plan. So what's the plan for once you elect the assembly in terms of confirming the condition of the assembly? Visual examination? Making sure you can go down.
Yeah, it's undamaged fuel base. Right now, I think the plan is visual inspection and sniffing. Make sure there's no gas leakers. Keith, does that sound right? Yeah, visual inspection.
These assemblies all come from clean cores.
As far as I know.
Or individually sick. Or UT.
All intact. No leakers there. There is a thought. We can distinguish the airline
I gather between the knowing whether it was a clean core or not, and then individually sipping it and doing UT, they're basically not even going with the airline, they're going with intact assembly, not undamaged assembly. Intact. No communication between the inside and outside of the pin.
Okay. So, that in terms of the staff contain, healing sampling, if there are fission gases shown, then probably this is not going to grow structure.
They're not going to have any rods in there that have any rods that are not intact. All the rods will have intact cladding, as far as I'm gathering.
Right. So that's the goal. Yeah, that is the goal.
And you're going to judge that by sipping or UT the core evaluation. The core
That's what I
evaluation.
was asking. It's one visual examination.
So you know my position on visual examination, that it's not worth very much because you only see 80% broad surface. So I would be having more on the other three types of examination. Telling me that you looked at it and you saw nothing.
Let's take it tomorrow. Okay. That's fine.
So the marketing, colon, and sirloin. You have one circular floor, one flat sirloin, rotating circular for those four.
In the center, right.
And everything else is one part of the sirloin.
Right.
So, PWR 17 by 17. Thank you.
Then you want to move on. We're already an hour into.
Okay. Okay, no other questions on the simplest one? Anybody on the phone?
Yes, this is Stephen Dolly with Platts.
Yes.
Oh, hello?
Yeah, go ahead.
Well, first I want to thank everybody for the efforts, but still I'd say about 80 to 85% of this is completely inaudible on the phone. I understand you're doing your best with moving mics around and everything, but just as feedback, it's almost impossible to hear folks who are not right on the mic. With that in mind, I apologize if this was discussed, but I honestly couldn't tell what different clad and fuel types are going to be represented in the cask, or if that hasn't been finally decided yet, when will you decide?
Oh, we already talked about that, so we're not going to cover that anymore. Just kidding. We have 4 candidates.
Sorry, this is who?
This is Ken Thornton. So tell my boss Ned about that. Keep going. Yeah. So 4 candidate assemblies in the middle of the cask are Zerk 4s, low tin Zerk 4, Zerlo, and M5. And then around those high burn-up assemblies, we have what we're calling a blanket of assemblies that are shorter cooled fuel, so they have a higher decay heat to help drive up the temperature.
And which will they be?
Those are M5 and Zerlo.
Okay, so in the middle, Z4, is it? Z as in zebra 4, Zerlo, and M5?
And a low tin Z4.
Low tin Z4, and in the blanket around the outside with the less cooled, hotter stuff, you got M5 and Zerlo?
Yes.
And did I hear someone say they'll all be from 17 by 17 assemblies?
That is correct.
Okay, thank you very much.
Welcome. Okay, well, let's move on to thermocouple locations and calibrations if we can. And John, I think I'll go ahead and just turn this over to you and talk about
You might grab that. Oops. In the shape of.
Okay, so basically on our thermocouple selection process, we have 7 ports where thermocouples will be inserted. Each thermocouple will have 9 measurement zones, so you got a total of 63 measurements. We have 2 in the central zone. We have 2 in the blanket region, and then we have 3 in the most outer ring of the fuel zone within that canister system. And the distribution of lance locations and how they've been selected axially is to provide a good mapping of the various locations within the canister system so that we can benchmark our thermohydraulic codes. Basically, that's really about. There's not much more to say on that unless there's actually some questions. We do have our hottest fuel assembly, or where our hottest pin location will be instrumented, so we believe we can pick that one out. And then the rest of them have been chosen to give a good representation in various locations within the cask.
I'm not quite sure what you mean by very good locations within the cask.
I'd really like to see at least one axial location where you think it's going to be the hottest point on the hottest pin.
We have that.
Also, for that same rod, I'd like to know how much the